So today we're going to go ahead and talk about uniform circular motion. So first thing I want to talk about is a little example. So imagine if we have a marble that's in like a circular tube right here, and all of a sudden the walls of the tube disappear. What direction would that marble go? Would it go direction A, B, or C? Go ahead and think about it, and then I'll check back in. Okay, so the marble would actually go direction C because there's nothing holding the ball in to keep it moving in the same manner. So direction C is where it would go. Interesting. And I think of it as like there's no force of the wall pushing it inwards. So I think of that as that's like our velocity in uniform circular motion. It is going to be tangent to the object itself. Cool. So let's go ahead and talk a little bit more about uniform circular motion. So this is just any type of motion where the speed is constant. So an object is moving in a circle at a constant speed. So I want you to think to yourself, if an object is moving in a circle at a constant speed, is it accelerating? Okay, if it's moving in a circle, it is changing directions, so it is accelerating because an acceleration is a change in velocity for a change in time. And if the direction it moves changes, then it accelerates, even if the speed is constant. Okay, good thing to know. Okay, so the period T, that is just the time for one revolution all the way around a circle. So if we have a circle and it's the time it takes for something to go around once. Let's think about units for this. It is a time, so the units of period are going to be seconds per revolution, or you could say like seconds per cycle. Any of those things would be totally great. Or sometimes people just put good old seconds, not seconds per, whatever it is. One revolution or one trip, you can think of it as. Cool. So now let's go ahead and think about speed as something moves in a circle. So if we think about speed, our equation for speed is just distance over time. So the distance for something to move around a circle once. So if I go all the way here, all the way here, what distance is that? Oh, that is just the circumference of a circle, which is just, so that's circumference, if I can spell that word, over the time for one revolution. So the circumference is just 2 pi r, if here is the radius, over time for one revolution, it's just capital T period. So we know the speed or velocity for something moving in a circle is just 2 pi r over period. Cool. And units for that is just the speed, so it's like the distance units divided by the time units. So we'll oftentimes use meters per second for those units. Cool. Let's talk about centripetal acceleration, AC. Okay, centripetal acceleration, AC. So what words do we see in the word centripetal? I see the word at the very beginning, center. What centripetal means is it just means center seeking. So the centripetal acceleration, if something is moving at a constant speed, the centripetal acceleration is not changing the speed, it is just working to change the direction. So let's write that down. So it causes the direction to change, not speed. So that's a very important point. It is also called, centripetal acceleration is also called radial acceleration. You'll see both words used. So keep in mind, those words are going to be synonyms. Centripetal and radial acceleration. And I think centripetal is like center seeking, radial is along the radius, so kind of similar things. Cool. So the equation for centripetal acceleration is just going to be our velocity squared over radius. So AC, again, is centripetal acceleration. V is velocity, which we know we'll oftentimes measure that in meters per second. And R, I use capital R, that was lazy that I was using different R's, is the radius, which we'll oftentimes measure in meters. And again, acceleration, oftentimes we'll use the units meters per second squared. But again, for any of those, it could be a distance per time squared for acceleration. Cool. So let's go ahead and look at this picture and draw a couple acceleration velocity vectors. So let's say the object is moving counterclockwise. So let's go ahead and draw the velocity vectors at different points. So right here at this point, again, based on the example we just talked about with the pi tin, the velocity is going to be tangent to the circle. So the velocity is just going to be up like that. If we pick another point, velocity is just going to be tangent. The velocity is just always going to be tangent to the circle motion itself. Cool. So acceleration is, again, center seeking, pointing towards the center. So that, and if it's causing the direction to change but not the speed, it needs to be perpendicular to the velocity. So acceleration is just going to be pointing inwards like this. And that is our good old acceleration vector. Let's say we've looked at some different points to find the velocity vector. Right here at this point, is it going to be moving faster or slower than it is on the edge? What I think about is like a bunch of people at a roller rink, all holding hands, like moving around in a circle. Who's going to be going faster? The person on the edge is going to be going way faster than the person on the middle, just because they have to cover way more distance. So the velocity vector, someone closer to the inside, is going to be a lot smaller, while right when you get to the middle of the circle, everything's spinning around it, but it's not moving. So velocity would just be 0 in the middle. Okay, so let's go ahead and solve one problem together. So for this, I'm going to first read the problem and then draw a picture. So we have a helicopter of 4 blades. So let's draw those good old blades. And the radius is, so it's some sort of circle. Wow, what a beautiful circle. The radius is what? 3.4 meters? Okay. And it's rotated at 550 revs per minute. Revs per minute is like, that's like a rotation speed. Okay. So for A, we want to find what is the linear speed of the blade tip in meters per second. We want to find the radial acceleration, which we know that's the same thing as centripetal acceleration, which is AC. We also want to find the period. Okay. There's multiple ways we could go about it. So linear speed in meters per second. So let's see. Let's look at this. So velocity is 550 revs per minute. So we need to somehow convert this revs per minute to meters per second. So let's think about how we can convert that. So first thing I think about, I easily know how to do minutes a second. So 1 minute is 60 seconds. So those cancel out. Let's now convert revolutions to meters. So let's think about it. 1 revolution to go around once, 1 revolution, that it looks like that is just the circumference. So 1 revolution is the circumference, which is what? 2 pi r, and r in this case is 3.4. So then revolutions and revolutions cancel, and we're left with meters per second. And I got 195.8 meters per second for the velocity. Cool. So let's go ahead and look at B. I should box that answer. B, radial acceleration, which again, another word is centripetal acceleration. And that is just v squared over r. So v is what? 195.8 squared over r is what? 3.4. And I got 11,278 meters per second squared. Cool. Let's go to the last part. So we want to find the period in seconds. So one way I could go about this is use velocity equals 2 pi r over t. Again, speed is distance over time, distance for a circle circumference. And we could just plug everything in, 195.8, and we could plug in radius and solve for t. One other way I want to do it, just to kind of mix it up, is we know period is seconds per revolution, correct? Okay. So we were given at the beginning 550 revs per minute. We essentially want time per revolution. So I'm just going to flip that or invert it. So the period is essentially for 550 revs per 1 minute, it is going to be 1 minute per 550 revs. So we have revolutions on the bottom, which is what we want for period. We now need seconds on top. So I can just convert 1 minute is what? 60 seconds? Cancel, cancel. And I get 0.109 seconds. Cool. Thanks for watching.